Good afternoon. I will be going through the practice midterm homework assignments. So this is for your midterm number 3, which is your last midterm of the semester. All right, so the first question is related to a Lewis structure. Okay, so NO2 minus. And so we have to first find out how many valence electrons. So we've got 5 for the nitrogen, 6 times 2 for both of those oxygens, and then another 1 for the minus charge. So what is that? So 12, 13, and 5. So that's 18 valence electrons. And so then you draw with singles. So we've placed now 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18. Okay, and then you say that, well, the nitrogen doesn't have an octet and it absolutely has to have one. So then you can do one of these numbers. Okay, but you could also have the double bond in this one. Okay, so you have a resonance form, and so that means then that you will have 2 identical bonds intermediate between a single and a double. Okay, so the real Lewis structure is really a hybrid between, this bond, for instance, is between a double and a single. Okay, and same with this one, it's between a single and a double. Okay. A chlorine atom in Cl2. So that's the Lewis structure of Cl2. And in this case, it is nonpolar. It is a nonpolar covalent compound or molecular compound. And that means that you don't have a charge, right? It's the same atom on either side of the bond. And so you don't have one that's going to be a positive charge, the other side being negative. If you had this one, now you'd have a delta charge there and a delta positive there, because this is more electronegative. Okay, so this would be polar covalent. This is nonpolar covalent. Okay, so that's a nonpolar covalent bond. Okay, neutral sulfur atom. So sulfur is in group 16 or 6A, not G, 6A. And so there are 6 valence electrons. Increasing wavelength. Okay, so as you increase wavelength, the energy will go down. Okay, and so this is going to lower energy radiation. And so microwave is the lowest, followed by infrared, visible, and then UV. Okay, so in this range, you are increasing wavelength, you are decreasing frequency, and you are increasing, you are decreasing energy. Okay, so remember, energy is proportional to frequency. Energy is inversely proportional to wavelength. Okay. Next question, formal charges to each atom in the resonance form. Okay, so chlorine is going to be, its valence electrons is 7 minus 1 bond right there. And then you've got 1, 2, 3, 4, 5, 6 dots. So that is 0 formal charge. This oxygen is going to be 6 minus 2 bonds and then another 4 dots. So that's also 0. And then this chlorine is going to be the same as this one. Okay, so everything is a 0 formal charge. Atoms of which element, indicated by letter, have this orbital filling diagram? So this is your n equals 1, 2, 3, 4, 5, 6. Okay, so you've got 6s2. And then remember, you go to like the 5Ds here. So that's your 5D. And then you've got your 4 Fs, okay? And so you could say that it's 6s2, 5d1, and then remember these Fs go in right in there, okay? And then like 4f3, okay, something like that. Okay, so that, it could be this, okay, or oftentimes these d electrons will all go into the F shell. Okay, so it's 6s2, 4f4. Okay, so irregardless, D is the right answer. Okay, all these other ones will not have any Fs, okay, any electrons in the F shell. So these are going to have like 3Ds. These are going to have, this one is going to have 3D and then 4P something. Okay, so the only one with Fs has to be down here in the lanthanide series. Okay. Electron dot structure of carbonate. Okay, and so carbonate has, so you've got 6 times 3 is 18, and then another 2 for the charge, and then 4 for carbon. So that's 24 valence electrons. So that's 1, 2, 3, 4, 5, 6, 9, 10, 12, 24. Okay, and then you say that carbon needs an octet, so then you do like that, let's say. Okay, and then you can do the double bond up here, or you could do the double bond, I guess, over here. Okay, so all the different resonance forms, and so your resonance structures will have 2 single bonds and 1 double bond. Okay, and there's 3 resonance structures. Okay, just the different positions of the double bond. The energy of light, and this is very typical on the exam. I'll give you the formula and the constants as well. Okay, and so this one is, you just kind of plug it in. And that's 2.99 meters per second. So the seconds cancel. Excuse me. Okay, and then your bottom is in nanometers, but the speed of light is in meters. And so a little trick is you can put this in as 410.1 times 10 to the minus 9 meters. I know that's not proper scientific notation, but it kind of saves you from going the wrong way, like going 4.101 times 10 to the minus 11 or something if you go the wrong way. Okay, and now the meters cancel, and so you'll end up with just so many joules out of that. Okay, so you just calculate it out. All right. Now, how many lone pairs are on the atom in the middle? Okay, so this is going to have 5 valence electrons from the phosphorus, and then 7 times 3 for the fluorines. So that's 26 valence electrons. So 6, 10, 11, 12, 4, 25, 26. Okay, and that is 1 lone pair. Okay, there are 2 electrons, but it's only 1 lone pair. Okay, a pair of electrons. How many lone pairs are in this one? And so this, you have 7 times 6 is 42. That's for all the fluorines. Then you've got 8 for the xenon. So that's 50 valence electrons. So then do your, like that. It really doesn't matter how you put all the periphery atoms around it. When we get to VSEPR shapes, then it does matter. But at this point for Lewis structures, it really doesn't. So we've now placed 12 electrons. 18, 36, 44, 42, 44, 45, 46, 47, 48, 49, 50. So one lone pair on the central atom. How many unpaired electrons are in cobalt in its ground state? And so let me pull up a periodic table. There we go. So cobalt is right in the middle there, element 27. And so it's going to be argon's configuration. Oops. Right here. So cobalt is going to be argon. And if we go back, then 4s2, 3d, and then you just read across. 1, 2, 3, 4, 5, 6, 7. Okay, so then to put those in their right orbitals, we have the s2, and then we start to fill in according to Hund's rule. We do 1, 2, 3, 4, 5, 6, 7. So that means that there are 3 unpaired electrons. Okay. Which is larger? Okay, so remember that atoms are bigger than their cations, and anions are bigger than their neutral atoms. Okay, so selenium 2 minus is bigger, and chromium is bigger than chromium 3 plus. Decreasing first ionization energy. Okay, and so the trend is that ionization energy will increase as you go left to right in the periodic table, and ionization energy goes down as you go down a group. Okay, so if we look at sodium, calcium, rubidium, I wonder if I can get this on a side screen here. Oops. Guess I can't. But if we go back to periodic table here, okay, we've got sodium, calcium, what other ones? Sodium, calcium, rubidium, chlorine, and helium. Okay, so amongst all these, helium is the noble gas, and so that's going to have the highest. And chlorine is right next to it, so that's going to be the second highest. Okay. And so then you're kind of looking, okay, so far that's these ones. I guess that's really the only, I guess that's as far as you would need to go for this question. But then next is, then you're looking between really calcium and sodium. Okay, and so if you go to the periodic table, you see calcium is lower than sodium, so that means it's going to have the lower ionization energy. Okay, and then you go to sodium is next. And then I think it's, so calcium would be, I guess, yeah, so calcium, if you look at that, so calcium is further to the right of sodium. So that's why it has a higher ionization energy. And then you go to sodium, okay? And then rubidium is down the group, and so that's going to have the lowest. Okay, so I would look at this and say, it's easy to pick the ones that have, the most as a noble gas, and then look for other non-metals, and then between the metals, look at the one that is farthest down in the periodic table. Okay, and so dig down a group, and that is going to have the lowest. Okay, and then it really boiled down to just between calcium and sodium. Okay, and the reason why calcium is bigger is because it lies farther to the right. Okay, it's actually down and to the right, but the biggest effect is going to be left to right versus top to bottom. Okay. All right. Which has the highest electronegativity? So you're just looking for which element is closest to fluorine. And so sulfur versus arsenic phosphorus. So sulfur is right next, and then arsenic, phosphorus are further to the left. So they're farther away from fluorine, and scandium is way over there. And so these are farther to the left. And so those are less electronegative, so that's closest to fluorine. Which has the smallest radius. Okay, and so with radius, as you go down a group, radius goes up. And as you go left to right, the radius goes down. Okay, so between, I guess, the metals, magnesium and strontium. So strontium is going to be bigger than magnesium. Okay, but all those are going to be smaller. They're metals, so they're, they're going to be bigger, right? So you're kind of exploding this one, right? So they're going to be bigger. And so then you're looking at the non-metals are going to be the smallest, and it's between tellurium and sulfur. And tellurium is at the bottom of the group, so that's going to be bigger. So sulfur is the smallest. Okay, so I guess you first apply that to rule out the metals, and then the second one is you look in this group, in the non-metals, and that's higher in the group, so that means it's going to be smaller. The highest first ionization energy, and so again, closest, so I guess you're looking left to right is the highest ionization energy, and bottom to top of a group also is going to be highest ionization energy. Okay, and so if you look at those, so left to right is really kind of between these two, and then you're looking in the group. Fluorine is higher in the group, so it's going to have the highest energy. Okay, this is some AM station, and it's got 1290 kilohertz. So remember that hertz is the same as seconds to the -1, okay, which is the unit of frequency, or nu, okay? And so you want to do the wavelength, and so the formula here is C is equal to that times that. And so wavelength is C divided by frequency. And so that would be 3.0 times 10 to the 8th meters per second, divided by frequency is in kilohertz. So that means like 1,000 hertz, right? So you could again say it's 1290 times 10 to the third hertz, or seconds to the minus 1, I guess. So it'll cancel. Okay, so those go away. All right, and so you end up, if you calculate this out, you end up with 232 meters. Okay, so 3 times 10 to the 8th, and then you've got 1290, and this comes because it's in kilohertz. So kilo means 10 to the third. All right, the compound ICl. Okay, so chlorine is more electronegative, so that means it's going to be a negative charge. That's going to be positive. Okay, so this is a polar covalent bond because the atoms are no longer the same. Okay, so you can compare that with the earlier question where you had Cl2, that was nonpolar covalent. The greater the electronegativity difference, the greater the ionic character. Okay, so if you look at kind of the extreme case would be if you have like a group 1, like sodium, and a group 17, like fluorine, right? That is total opposite ends of the spectrum, so NAF. This is an ionic compound. Okay, versus if you have like FCl or something, those are 2 nonmetals. Now that's a molecular compound bonded together with covalent bonding. Okay, so the greater the difference, the greater the ionic character becomes. The greater the energy, the shorter the wavelength. So again, I think we already talked about that, but or it's proportional. Inversely proportional to wavelength, energy is proportional to frequency. Okay, so yeah. So it's asking greater the energy, then frequency will be higher and wavelength will be shorter. Okay, so this is lithium, beryllium, barium, or boron, and fluorine. Okay, so you're going across, you're going left to right in that period. Okay, and so the size will decrease. Okay, so that means then that fluorine is going to be the smallest. Beryllium, okay, is, I guess, so the biggest here is going to be lithium, okay, because that is farthest to the left. And then you're going to be beryllium, boron, and fluorine, okay? So that's the smallest because it is farthest to the right. And this is farthest to the left. Okay? So sphere C is for beryllium. Now, this is in the group 15. Okay, so remember you've got like nitrogen, phosphorus, arsenic, antimony in the group 15 block. Okay, and so now as you go down a group, it's going to get bigger. So this would be antimony, arsenic, phosphorus, nitrogen. So it's asking which is antimony. It is going to be D. Okay. Krypton is 1s2, 2s2, so you just read it across. Okay, so xenon should be 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, 3d10, 4p6. Okay, so 4s2, 3d10, 4p6. So that would be krypton. And these waves, okay, so wave A has the shorter wavelength. Remember, wavelength is the distance between crests or troughs, okay? And so I think you'd agree that this distance is shorter. Okay, so that wavelength is shorter. And then therefore energy is inversely proportional. So if you have a shorter wavelength, then it's going to have a higher energy. Possible values of L. So remember, if n is equal to 5, then L can take values all the way from 1 to, or actually all the way from 0. Whoops. From 0, 1, 2, 3, and 4. It's all, so L, in other words, can go all the way from 0 to n minus 1. Okay? So these are the only values. It can't take, this is talking about m sub L. Okay? So just integers from 0 all the way to n minus 1. What are possible values of n and m sub L for an electron in a 5d orbital? So remember, if we have s, p, d, f, then your L's are 0, 1, 2, 3. And so a 5d orbital, then n is equal to 5. L is going to be equal to 2. Okay, and then m sub L can take values all the way from minus L, in this case 2, 0, 1, and 2. Okay, so those are the values for the different quantum numbers. A quantum of light, this is just kind of a definition. It's called a photon. Okay, so a photon of energy equals a quantum of energy, it's often known as. Okay, so just kind of a definition. So when we, for instance, when we calculate this or this, depending on what you're given, we would say the energy of a photon is very typically what the question will state. What is the frequency of that light? Okay, so again, like that. So you want to know frequency, so it's c over lambda. And so then you have speed of light divided by wavelength, 632.8 times 10 to the minus 9 meters, if we do it like that. Okay, then you end up with, let me just verify, but you should end up with that. So 3e to the 8th divided by 632.8 e to the 9 minus. Yeah, you end up with 4.74 times 10 to the 14th seconds to the minus 1, or hertz. It might also give the units in terms of hertz. So neutral alkaline earths, okay, they will be S2, right? Like magnesium, beryllium, they will have, like, for beryllium will be whatever helium is, 2s2. Magnesium will be neon, and then 3s2, okay, etc. Okay, so they will be an S2 configuration. So for instance, beryllium is helium, 2s2. Okay. Ground state configuration of selenium, 2 minus. And so if you add 2 electrons to selenium, you get krypton's configuration, right? So selenium has 34 electrons, Se2 minus has 36. Okay, so it's going to be krypton. And so that is argon, 3d10, 4s2, 4p6. Okay, so 4s2, 3d10, 4p6. Covalent bonds, so that is going to be between nonmetals. And that includes hydrogen also. Okay, so HCl. That's ionic. This is ionic. And then that would be ionic. That's covalent. Okay, but yeah, this is wrong because both of those are not covalent, right? So if you have a metal plus a nonmetal, that will be ionic. Okay, which contains ionic bonds. So again, so you're looking for a metal and a nonmetal. These are two nonmetals. Those are two nonmetals, and that's the same thing. It's two nonmetals. Okay, so which Lewis structure for that has a formal charge of -1 on the most electronegative atom? So let's look at these. So in this case, oxygen would have 6 minus 1, 2 bonds, and then another 4 dots, so that would be a 0. Nitrogen is 5 minus 2 bonds, and then 1, 2, 3, 4, so that's a -1. This one, you've got 6 minus 1 minus 6, so that's going to be a -1. And that nitrogen is going to be 5 minus 1, 2, 3, 4, 5. Or I guess 3 bonds and then 2, so that's 0. In this case, that's 4 minus 1, 2, 3, 4, 5. There's 3 and then another 2. So that's a -1. The nitrogen is 5 minus 1 bond, and then 1, 2, 3, 4, 5, 6. So that's a -2 in that case. This oxygen, the middle one, is going to be 6 minus 1, 2, 3, 4. So that's +2. And then in this case, you've got 6 minus 3 bonds, another 2. So that's +1. The middle carbon is going to be 0. And then nitrogen is going to be 5 minus 1 bond, 1, 2, 3, 4, 5, 6. So that's a -2. Okay? And in these cases, that carbon is going to be 0, and this is going to be 0. Okay, so looking at all those charges now, oxygen is more electronegative than nitrogen. Okay, so you're looking for, in this first case, it's saying nitrogen has the -1 charge. Okay, so that's not correct. So that one's wrong. In this one, we've got the minus charge on the oxygen, so yep. In this one, we've got minus charge on the carbon, so that's not going to be right. And in this case, we've got a -2 charge on a nitrogen, and so that's again not right. And so -1 on the most electronegative atom is that variety then. Okay. Which can accommodate more than 8? It's really anything in the 3rd period and below. And so we're looking at like things like silicon, phosphorus, sulfur. Okay, and so you look and phosphorus is there. So that's in the the 2nd period. And so that can't. That's the 1st period. So for sure not. And that's the 2nd period. And so that can't expand its octet. And so that's the 3rd period. So which has, so starting from xenon, and then you go 6s2, 5d1, 4f7. So xenon, 6s2, 5d1, and then you read across 7. 5, 6, 7 is gadolinium. Okay, so just kind of read it off the periodic table there. which element has the most favorable, which means most negative electron affinity. And so with electron affinity, remember that this is adding electrons. So that would be things like that, plus an electron to give you this. Okay, and it is going to be most preferable. So in other words, the most negative value as you go to the halogens. Okay, so out of this group, the least favorable will be things like a metal. Okay, way on the left side. Okay, so as you go left to right here, the electron affinity will increase, except for noble gases. Okay, they don't want to add any electrons at all, so they will have a really low value. And so out of these possibilities, we've got a metal, so that's not going to happen, another metal, a noble gas, or something that is pretty close to the halogens. And so that's going to have the most favorable affinity for an electron. So which is an S block element. So those would be either group 1 or group 2. So this is so these two are the S block. This is the D block. This is the P block. And then these guys are the F block. Okay. So B A is the answer for that one. Which has 2 unpaired p electrons. Okay, so if we kind of draw these out, for A, so let's say here you've got boron, carbon, nitrogen, oxygen. So if we do it for boron, we're going to have like the 2s and then 2p here. Okay, so boron is just going to have that. Okay, so it doesn't have 2 unpaired electrons. Carbon looks like that. Okay, so B is definitely a possibility. And then nitrogen looks like this. Okay, so it has 3 unpaired electrons, so that's a no. And then let's go to like group D on there, which is oxygen, and that's going to look like this. So we now have to place 4 electrons, 1, 2, 3, 4, and that leaves 2 unpaired electrons. Okay, so both A and, so both B and D will have the possibility for 2 unpaired electrons. Which ionization process requires the most energy? So the first electron is always the easiest. So that will have, in this relative sense, so it'll have the lowest ionization energy. Then when you start to remove that second electron, that'll have the second lowest. And as you start to remove more and more electrons, that is going to require the most energy, because you're trying to pull an electron away from something that is a +3 charge. So those electrons are really tightly bound here. Okay, so IE1 is going to be less than IE2, is less than IE3, is less than IE4. Okay, the 4th electron. The longest bond, okay, so single bonds are going to be the longest and weakest, because you only have 2 electrons in between them. Okay, the shortest and strongest is going to be triple bonds, right? Because you have 6 electrons between those atoms. Okay, the most acceptable dot structure for hydrazine here. So we count up valence electrons. So we've got 10 plus another 2 for the hydrogen, so 12 total. Okay, so we do something like that, where it's kind of symmetric. And then, so we've now placed 1, 2, 3, 4, 5, 6, 7, 8, let's say 9, 10, 11, 12, okay? And then you say that that nitrogen doesn't have an octet. And so you can do maybe something like that, okay? And so this now, everything has an octet. Hydrogen is, of course, stable with just 2 electrons between them. And the nitrogens, both of them have an octet. Okay, and then looking at formal charges even, everything is 0 on here. Hydrogens and the nitrogens are all 0. Okay, so that's the most stable. The most polar bonds, and so you're looking for the biggest difference in electronegativity. And so carbon versus hydrogen. In the periodic table, hydrogen is way on the left and carbon is way on the right. But as far as differences in electronegativity, you really consider hydrogen like a halogen. Okay, so you don't have that huge difference in electronegativity there. And then carbon versus nitrogen, so they're right next to each other. What's the other one? Carbon versus oxygen, okay, a little farther away. And so the biggest difference in electronegativity is going to be between carbon and fluorine, okay, the most electronegative. Okay, so has the greatest difference in electronegativity, therefore the most polar bonds. Okay. Which has the weakest bonds. So as you go down a group, the orbital sizes get bigger. And so if you look, that's maybe fluorine, and you have chlorine, bromine, and then iodine, let's say. Okay, and so if you're thinking of overlap between carbon in each of these cases, we keep that the same size. So everybody see, as you go down the group, these orbitals are getting bigger. And so you're starting to only get overlap on really a small little area here. These spheres can only overlap on a small little dot, versus if you have smaller orbitals overlapping, they have a larger area where those orbitals can overlap. Okay, and that makes these bonds stronger. Okay, and as you go down, then you have weaker bonds. Okay, so Ci4 has the biggest so it has the biggest atom is iodine that's overlapping, and so therefore the weakest bond. Okay, which are allowed resonance forms of NCS? And that's really drawing it weirdly here. But yeah, if you're looking at 1, you're moving the double bond or multiple bonds around, so you're moving between a triple and a double and a single here, so that looks right. If you're looking at 2, and I'm going to have to draw these out properly here. Okay. Whoops. CS. That and this. So this is the first one. Okay, and then the second one is this. Again, with all the dots. And then we've got that. Okay, and then the third is again the same one. And now we've got this. Like that. Okay, so I think I talked about this in the last lecture too. And so in this first case, does everybody see that, hopefully, that we are just moving the multiple bonds around? Okay, so we're moving kind of this one there, and then this one here, okay, to give you that other resonance form. So that definitely is resonance. The second one, you're doing the same thing, really, so you're moving that there. But the problem here is that carbon has more than an octet, right? So that can't happen. And then in this last case, all we've done, it's actually the same thing. Okay, so we've just written it the opposite way around. So we haven't moved any bonds, okay, around, and so that's not resonance. Okay, so it's really only one is allowed resonance forms of that ion. Okay, which would you predict to have an anomalous or an atypical ground state electron configuration? And so remember, the exceptions are ones like copper, silver, gold, okay, because those, for instance, copper, or I guess this is asking for silver here. Okay, so silver, we would expect it to, if you look at a periodic table, I'll look at a table as I'm doing this. So silver, you would expect it to be krypton's configuration. And then it would be, what's that, 1, 2, 3, 4, 5 S2, 4D9. Okay, but remember that configurations are most stable if they're either fully filled, half-filled orbitals. And so this becomes then krypton 5s1, 4d10. Okay, so that is anomalous. Versus cerium, that just, follows the general rule. That's not an exception. Strontium, also not an exception. Selenium, not an exception. So really the exceptions will be the coinage metals. So you're looking at copper, silver, gold. So these like D9 configurations. And also we've got chromium, molybdenum, tungsten. So the D4 configurations. Okay, so those will become D5, like a S1 D5 configuration. These will become S1 D10 configurations. Okay, so those are really the only anomalous ones that we talked about in this class. There are others in the lanthanides, actinides, but we're not going to go into those. And then here is anomalous ground state of chromium. So chromium is one of those where it would be argon, 4s2, 3d4, okay, but it likes to do the S1 3d5 so that everything is half filled. Okay, so it's that configuration. Ground state of oxygen. Okay, so it's helium, 2s2, 2p4. So the way we write those in again is 1, 2, 3, 4. Okay, so that filling by Hund's rule. We keep the maximum number of paired or parallel spins. And then the Pauli exclusion principle says that no two electrons can have the same set of quantum numbers. And so things like that would be like this. Okay, if they're both spin up or something like that. Okay, so this is the case where Pauli exclusion principle is violated. That should be like this. Okay, so one has m sub s of plus 1/2. That has a spin of minus 1/2. Okay. This one, yeah, we talked about in lecture. So you're looking at ionization energies, and they're going up. So as I said, as you are removing more electrons, they go up. And so, it's increasing, 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 and then it like jumps a huge amount, right? It's a big, big difference between those two. And so what that's really saying is that this would like to lose, or it could lose 3 electrons, but good luck ever losing the 4th or the 5th. Okay, so whenever you see this huge jump, that means that it will like to form, in this case, a 3+ charge, right? Because it can lose 3 electrons, but never the 4th. Okay, and so that would be aluminum. You're looking for something in group 13. Okay, if, for instance, you see something where you've got, maybe using these numbers, 578, 1817, 2745, 3691, and 14,000 or something, that tells you it could lose 4. And so that would be things in like group 14, like silicon, for instance. Okay. And then the last question, which two ions have the same electron configuration? And so rubidium, cesium, if we look, they're both as plus charges. So rubidium plus is the same as krypton. And then what was the other one? I forget. Rubidium and cesium. Okay. So rubidium is krypton. Cesium plus is xenon, so they're not the same. Okay, so what did we say? Rubidium plus, if I look at a periodic table here, rubidium plus is the same as krypton. Cesium plus is the same as xenon. Okay, so those are different, so nope. Iron 2 and iron 3, no, they're different. Selenium 2 and iodine 1, this is the same as xenon, whereas selenium 2 plus is really like germanium, I think. Okay, so again, they're not the same. Whereas I minus is xenon, and barium 2 plus is also xenon, the same thing. Okay, so they have the same electronic configuration. Okay, we would say that they are isoelectronic. Okay, so we'd say that xenon, barium 2 plus, and I minus are all isoelectronic, as well as we could say tellurium 2 minus or thallium 3 plus. Okay, all those will be equivalent to xenon's configuration. Okay, all right, so those are the questions on the practice exam. Let me know if you have any questions about those, but those are the variety that you will see on the exam. So there'll be Lewis structures, resonance, formal charges, and then a lot on electronic configurations and some questions on those periodic trends like sizes of atoms, of ions, things like that. One other thing to look at are if you have a transition metal ion, how to do those configurations. And so, for instance, if we say chromium 2 plus, then just do the configuration of what the element itself is. And so let's pull up a periodic table here. Okay, so chromium is going to be, if I put both of these here, it's going to be argon's configuration, 4s2, 3d, 4. Okay, and then you can say then, the best configuration is what we saw was 4s1, 3d5. Okay. And so with transition metals, remember that the S's leave first. So here we have to remove 2 electrons, right? Because it's a 2 plus. And so first, to get rid of the S electron, and then you start to pull ones away from the D. Okay, so then if you lose 2 electrons, it's going to be argon 3d4. Okay, so we've lost that one as well as one from here. Okay. All right, so that's something else to be aware of for the exam. All right. Enjoy the rest of your day.